All right, so we're now going to talk about p-value because it's related to what we're going to do next. All right, and it's helpful to understand what p-value actually means. And well, how can I say this? It's just like most things here in statistics. It might not seem very comfortable or familiar to start off with, but eventually, hopefully, it will. When we ask the question, what is p-value? What does p-value actually tell me? I'm just going to try to go back to what we did last time. I said the word p-value, and I said p-value is, and then what did I say after that?
Variable.
What?
Wait.
No. Okay, so you're not going to do that. Okay, good. Back off from that wrong answer. Good. Right? It's not variance. No, what is it?
Alpha as a variable.
It is alpha as a variable. So if we understand that alpha means it's my chance of being wrong, p-value means the same thing. The p-value is my chance of being wrong, or maybe better, the chance of a random fluctuation. Are these numbers different just because of a random fluctuation, or is there a real significant difference between these numbers? Is there an actual change in these numbers when I put them into the categories of blood pressure and hemoglobin, or is it just a little bit of a random thing? Okay. So then the question is, if that's the description of what p-value is actually getting us, it's getting us alpha as a variable, then the next question is, how do we find it? Okay. Now that I know what it is, how do I find it? Somebody tell me that. How do I find the p-value? No. It is the area of the tail. And what do I use to find the area of the tail? No, I do not use alpha to find the p-value. I use the test value. So what I'm doing here is I'm saying I'm going to take my test value. My test value is going to take me out from the 0, all right? It's going to take me out there somewhere. I'm going to look at what the area of that tail is. That will tell me the p-value that I need. Okay?
Where do you get the area from?
That's a great question. But I'm using my test value. I'm using this 9.7.
Critical value, you use the test value.
I do not use the critical value.
That's what I'm saying, instead of that, you use the test value.
That's correct.
And you go to the chart.
I do.
Nice.
I go to the chi-squared chart, yes. Okay? So I need to figure out where is 9.79 on the chi-squared chart. And then from there, I'm going to figure out something about the area of the tail. Okay? So I need my chi-squared chart. Let's make that happen here. Here's my table G, chi-squared distribution. So then the question is, where am I going to look? I know that my degrees of freedom is 4. So that's where I'm looking. I'm looking for my degrees of freedom to be 4. If I know the degrees of freedom is 4, then I'm going out here, and these numbers tell me the tail area. Okay? If my test value is 9.79, degrees of freedom 4, this would be the value if my alpha was 10, 0.10. So if I would make a picture here, and I would say I'm out here, and this is an area of 0.10, that would be 7.79. But I'm farther than that. I'm at 9.79. So here at 7.779, this would be associated with an alpha of 0.10. I'm farther out than that. Okay, what's next? 9.488. That's right here. 9.488. That would be associated with an alpha of 0.05. But I'm farther out than that. What's next? 11.43. Well, that's out here somewhere. I'm not that far. Okay, so my alpha is not smaller than 0.025. It's not smaller than any of these other ones here. So what can I say about the p-value? What do I know about this amount of area right here? All I know from this table is that my p-value is less than 0.05. That's all I know from this table. I know my p-value is less than 0.05. That's as far as I can get with my table. Okay?
Why is that less?
Because as I go to the right, this area of the tail gets smaller. And so this was my 0.05 area. I'm further out than that, so this is smaller than
Okay.
Okay? So my p-value is less than 0.05. Is that good news? For my purposes. I want it to be small. I want my amount of error to be small. So yes, that's good news. This is good. I have a small p-value. Small p-values are good p-values. Okay? So then, this is important for you to understand. How does p-value actually work? If the p-value is less than alpha, reject the null hypothesis. If my p-value is less than alpha, then I am able to reject the null hypothesis. That's it. Okay. How do I know what the p-value is? I look at the table based on the test value. How far do I go? Well, I go as far as I'm able to, all right? But all I really need to know is if I get past my alpha, if I get my alpha, or if I get an area smaller than alpha, if I go out there, way out there, and my p-value is getting smaller, and it's smaller than alpha, that's all I really need.
So none of the stuff, we're not really getting numbers, we're able to make decisions, right?
We're able to make decisions. For this particular problem that I just showed you right here, we're not really able to say anything much about the numbers. but we are able to say that there is a relationship, that something is affecting something else. That's all we know.
So this is a continuation of testing.
This is a continuation of test of independence. Yes, it is. But it's also true for anything else, okay? For any other problem, for any other research that anybody ever does, p-value is describing alpha as a variable. How did they find their p-value? They found the area of the tail from the test value. And so they want it to be small. If it's smaller than alpha, we reject the null hypothesis. Okay, so let's just do a little Google here. Blood pressure p-value smaller. Okay. New aspects in hypertension, adrenaline, whatever's. Okay. Let's find my p-value here. Oops, it doesn't want to give it to me. P-value. Oh, come on, you guys. Oh, here we go. The experimental data given in the text or figure are expressed by blah. The significance of difference was estimated by the t-test. A p-value smaller than 0.05 was considered. That's what we just said. A p-value smaller than 0.05 is considered to be significant. Hey, somebody else said it too. There we go. Results. There they are. See them all? Results. Oh, look at that. Ooh. Bisoprolol on dynamic exercise-induced changes of lymphocyte beta-2 adrenoceptor density. And so you can't say you didn't learn anything today, right? There you go. Okay. So what they're showing, oh, there it is. See this little double asterisk, this thing right here? They say P is less than 0.01. Same is true for this thing that has double thing. That's pretty common when you have something that's even better than 0.05. You'll put two asterisks on it, and you'll say it's less than 0.1. So that's even more confidence we can have in the result. All right, so that's what happens for p-values, and it's true for any kind of research. Having a small p-value means that they're pretty confident that it's not just a random thing, but there's an actual difference that's happening due to whatever. All right, so the last topic that we have is that we're not going to be working with proportions, nor are we working with frequencies. We are now going to be working with averages. So this is multiple comparisons, averages, or means, right? So what we're going to have to ask is some kind of a question that's related to a number. We're no longer looking at putting people into categories with yes/no questions. We're now asking people questions about money or blood pressure or something, okay? So what I have here is, and I'll zoom in on all this a bit. Okay, so what I'm doing here is I'm looking at amounts of student debt from students of different colleges. I have college A, B, and C, and I have their student debt amounts listed. So what does our data look like when we're comparing averages or means? We have categories with averages or means. So at this point, I'm not just saying what's the average for this college. I'm asking the question, what are the averages for all three of these colleges? Now, we need to think about this as being something like well, I need a different symbol here. I'm just using X, Y, Z just as three different variables here. So I'm measuring different colleges. I'm measuring the amount of student debt. This college is going to have a certain set of values. This other college is going to have another set of values. This college is going to have another set of values. Are there significant differences between these averages? Well, it kind of looks like it, right? But what if I had something look like this? Is there a difference in the averages? It's kind of hard to tell, right? Because they're all scattered. There's a lot of scattering in between these things. So what we have to do is we have to talk about what is the variation of the data. It's not enough for us to say that the numbers are different. We have to say, is the amount of difference within each data set, is that small? And the amount of variation between the data sets large? Because certainly we could have something look like this. That would be really clear. It's obvious here that there's three different things going on. Here, it seems like there's three different things going on. Here, we just don't know. So this is called, the thing that we're doing is called analysis of variance, which has another name, ANOVA. So this is ANOVA. That's a fun word, so we like to use it. So what we're looking at here, again, the question that we're dealing with, do we have different averages? The student loan money, it's scattered about in terms of some are numbers that are high, some are low, some are the same between the colleges. But is there a significant average or a significant difference in those averages? So here is our null hypothesis. Null hypothesis, mu sub 1 equals mu sub 2 equals mu sub 2. That all the averages are the same. What's the alternative? at least one use of I is different. So again, we're working with averages here, and we're going to say that the numbers come out to be the same. Is it possible that they just come out all to be the same? Or is there some group that's separate from the other data set? Can we find a difference here between them? So in order to do that, we use something called ANOVA. And this is something that happens on a computer where we just put stuff in and we hit a button and we say do ANOVA. Now, if we were looking at the averages, here are the different averages. Do I know for sure that any one of these averages is significantly different from the others? The answer is no. Just from this information that I have right here, I don't know which of those pictures I'm looking at. Are these things all just kind of mishmashed together? Or is there a specific one that is separate, not just based on the average, but on how spread apart the data is? So I cannot look at something like this and know right away that there is a difference. Even though these numbers are different, I do not know if there is a significant difference or if this is just a random fluctuation. This is just sample data. Because it's sample data, we can get no conclusion from it. The sample data by itself cannot tell us if there's a real significant difference here. So you need to understand that. That's important to know.
So no matter what the numbers say.
No matter what the samples say just by themselves, we can never draw a conclusion just based on this. But what can we do? Well, we can do something called ANOVA, and it looks like this. What does it tell us? We don't care right now about any of these numbers except the p-value. The p-value is the only number that we care about. None of the other stuff matters to us at all. All we care about is this thing. And all I have to do then is answer this question. Is the p-value less than alpha? If the p-value is less than alpha, I would reject the null hypothesis. Okay? If I take alpha to be 0.05, what happens?
You don't reject the null hypothesis.
I do not reject the null hypothesis. So Eric, what does that mean when I do not reject the null hypothesis?
No decision.
There's no decision. Amber, can you tell me what else I say when I do not reject the null hypothesis?
There isn't enough evidence.
I'm sorry, what did you say?
There isn't enough evidence
There's not enough evidence for what?
to prove the alternative.
There's not enough evidence to prove the alternative. So right now, what we have here is we say, even though those numbers did come out to be different, those averages did come out to be different, they are not significantly different. So that we would be able to say for sure that one college is different from another in their average amount of debt. Yes?
So if we don't have enough evidence to prove null or alternative, zero, no.
That's a one there, yeah, sure it is. Thank you. Yeah, mathematics is definitely better in a group than by yourself, because if you do it by yourself, you make a mistake. Thank you. So there's not enough evidence to prove the alternative. So what we're looking at here is we're saying it could be that there's a difference, could be that they're just fluctuating. I can't tell. Obviously, the sample numbers are different from each other. But there's not enough of a difference to say that it's a real difference. There's too much variation. It's like this picture number 2. There's too much variation in the data to say that one of them is different from the other. Can I do dot plot with this? I might be able to. Well, no, I'm not gonna. Okay. So that's the end of the ANOVA test. Okay, we do not reject. But I want to show you how the confidence intervals look. I have confidence intervals for the averages, and they look like this. Here are the confidence intervals for these different averages. And I have the numbers up here, but we'll just go with the picture for right now. Can we say that there is a difference between these averages? No, we can't say that they're a difference because the confidence intervals all overlap with each other. Is A less than B? We don't know because it could be higher. A could be up here, and B and C could be at the bottom of theirs, and so A could actually be higher than the other two. We just don't know. The confidence intervals are showing us that they overlap, so we cannot make a decision about whether one of them is higher or lower than the others, because they all overlap with each other. Okay. So let's look at a different possibility here. So this is the amount of expenses for a different school districts. Okay, this is their per pupil stuff. This is problem number 13 on page something or other. So I want to make sure I give you the right information here. Yes, this is the per pupil cost in thousands of dollars for certain types of charter schools. And so they've got these 3 different parts of Pennsylvania, and they say, are the per pupil costs, are they the same or are they different? So once again, the question is here, are these three averages the same, or can we say at least one is different? If I just look at these numbers, it sure looks like this one is quite a bit lower than the other two. But I don't know that for sure, because I don't know if this variation means that it's just way scattered, and these two are wherever. So based on just the sample information, I don't know if there's a real difference. But now I'm going to look at ANOVA. I don't need any of these numbers. I don't have to worry about where they come from. I don't have to think about them or compare them at all, except for the p-value. The p-value is the only number that I care about. Okay? So, Brianna, what can you tell me about the p-value?
I really can't tell you anything. I don't get it.
Okay, do you see where it says p-value?
On the board?
Yeah, on the screen.
0.0043.
That's correct. None of these other numbers matter at all. Only the p-value matters.
How did you even get that?
Does it matter? Not at all.
Everything is given to you.
Everything will be given to you. There's absolutely no calculation you're going to have to do. This is what you'll be given on the test. This is what you'll be given on the homework. What do you need to find? P-value. There it is. Do you need to calculate it at all? No. Are you going to use your calculator at all? No. What are you going to look for? The p-value. Once you find the p-value, will you need anything else? No. You don't need anything else. You don't need any of these other numbers. All you need is the p-value.
Less than.
It's less than 0.05. If alpha is 0.05, is this less than 0.05? Yes.
Are we just always assuming that it's 0.05?
We are.
Then you would reject it?
Reject what?
Hypothesis.
What does that mean?
That there is enough evidence to prove
What does that mean?
that.
Can you read the alternative hypothesis to me?
At least one average is different.
That's what we mean when we say prove the alternative. That means the alternative is true. At least one of these averages is different. Does that make sense?
Yep.
Okay. So when I get to that point, when I say, what does it mean to prove the alternative? I'm always going to ask you to read me the alternative hypothesis, because that's what it's proving. The alternative. At least one of these averages is different. How do I know that at least one of these averages is different? The p-value is less than alpha. The p-value is less than alpha, reject the null hypothesis, prove the alternative. At least one of these averages is different from the other. I'm right now done with ANOVA. That's all ANOVA can tell me. ANOVA just tells me there is something which is different. It does not tell me which one, and it does not tell me the direction of the difference. The only thing ANOVA tells me is that at least one of these averages is different from the others. But I currently don't know which one, and I don't know which direction that difference is. What's the difficulty in this problem? Number one, the null and alternative hypotheses. You have to know what you're actually talking about. What are we trying to prove? We're trying to prove that we have different averages between these different areas. I have a list of per pupil expenditures. Are there more expenses in area 1 compared to 2 or 3, or 2 compared to the other ones? I don't know yet. I'm trying to prove that there's some difference in the average for these numbers. That's this right here. Are they the same, or is there some difference? That's what I'm trying to prove. Most people don't get this. They don't know what the null hypothesis is for ANOVA. And so when it comes to that question on the test, they're not able to answer it because they don't know what they're looking for. ANOVA always has this null hypothesis and this alternative hypothesis. You have to keep track of that. Because on the test, when it gives you an ANOVA question, you're going to have to write this down in order to know what it is you're trying to prove. Then once you get to that point, there are no calculations. All you have to do is find the p-value. You look at the place where it says p-value, and you want to find out, is it less than alpha? If it's less than alpha, reject the alternative, reject the null, prove the alternative, read this. At least one of them is different from the others. And you're done with ANOVA. But until you know what this is, you won't be able to know what it is, how it works. You have to keep track of this. Once you keep track of this, it's very easy to do the problem. Look at the p-value, less than alpha, reject the alternative, state the alternative, you're done. All right, question out.
What's the I after mu?
Oh, that's just at least one of the mu's. Say just one of the mu's. One of the 3 that I have, or whatever. Okay. This is really not that helpful in terms of information. So we're not going to stop here. We're going to then look at the confidence intervals and see what they tell us. So we go down here and we look at the confidence intervals. What is the purpose of the confidence interval? Amber, can you tell me the purpose of the confidence interval?
To use a sample to measure population.
To use a sample to measure a population. What are we measuring here, Amber? We're measuring averages. So I'm looking at these confidence intervals. These confidence intervals are telling me where the actual population averages will be. I'm using the samples, and I'm finding from those samples the population averages. What do I see in these population averages? Do I see a difference? Do I see that one of these confidence intervals is actually separate from the others? Is there any of these confidence intervals that are either completely below a different one or completely above a different one?
Not both, just one.
It can be whatever.
Above area.
Area 2 of mu sub 2 is higher than this, greater than this.
Doesn't contradict our.
No, our decision was at least one of them is different.
Oh.
So our decision said that there is a difference. And now we know what the difference is. Area 2 spends more money per pupil on average than Area 3. What about Area 1? We don't know. It could be higher or lower than any of the others because those overlap. There's just not enough of a difference between area 1 and the others to say anything for sure. But we can say that the average, population average for area 2 is greater than the population average for area 3. Once again, the ANOVA procedure, once we go through it, tells us that something is different. Some average is different from some other average, but we don't know. But once we get to confidence intervals, now we can actually see that specific difference. It's not 1 and 2, it's not 1 and 3, it's 2 and 3. 2 is higher than 3. And we can have confidence in that result because we have confidence intervals. They're telling us where the stuff actually is. Where is that population number? That's why, again, a lot of people say confidence intervals are the real way to make statistical decisions. Because by using ANOVA, we just said there's something going on. But confidence intervals give us more information, and it's more useful to us to say, you people are spending more money than you people over here. And for area number 1, we're like, well, we don't know. We'll need more information about what's going on. Okay? So, what's going to happen on your homework is that you will have just a printed out version of these things based on certain problems, one of which just comes from a data set, another one which comes from problems in your textbook with different pages. So then what you'll need to do is look at what's in there. You will look at the ANOVA part of the problem just by looking at the p-value compared to alpha. Then you will look at the confidence intervals to see if they are separate from each other. This is not the same as goodness of fit. You don't have a given list that you're comparing to. You're actually comparing these intervals to each other. And you see if there's one that's higher or lower compared to the other. And that's it. All right. I'll plan to see you on Wednesday.
Give it back to you at the end of class. Sad that I've already.
Never do that.